So, I want you to imagine a star that doesn't actually burn. It's completely cold, totally dark, but it's so massive that it's bending space and time all around it. Today, we're going to go on the hunt for these phantom objects, venturing into the super strange theoretical world of solitonic stars. We think we have a pretty good handle on our cosmic neighborhood. We see the brilliant fires of stars, the gaping voids of black holes. But what if that's just the stuff that's easy to spot? What if the universe is jam-packed with other, much weirder inhabitants, hiding out in the shadows between all those lights? Well, a lot of theorists think there might be a whole menagerie of these hidden objects out there. They've even got this fantastic name for them, exotic compact objects. And we're not just talking about another type of rock or gas cloud here. This is like a cosmic zoo full of bizarre, powerful entities that seem to be made of stuff straight out of science fiction. So what makes these cosmic creatures so fundamentally alien? For starters, they don't burn at all. There's no nuclear fusion going on like there is in our sun. Instead, they're held together by these really strange quantum forces, which means they could be these pristine relics from the dawn of time itself. And, okay, here's the big one. They could actually be the dark matter that astronomers have been searching for decades. Okay, so to understand these bizarre stars, our whole investigation has to start with their fundamental building block. And it's this wonderfully weird and elusive thing. Particle doesn't even feel like the right word. It's known as a Q-ball. So what in the universe is a Q-ball? Right, forget about protons and neutrons for a second. Imagine a ripple in a pond that, because of some quirk in physics, just holds its own shape forever. That's kind of what this is. It's a self-contained bubble of pure energy, a persistent wave that physicists call a soliton. And it's kept from just fizzling out by a special quantum property, this charge Q, that basically locks it into existence. This theory, which was proposed by the physicist Sidney Coleman, suggests that this little energy bundle is fantastically stable. And why? Well, because the universe is, you could say, lazy. The energy locked inside the Q-ball is actually lower than if all its parts were flying around free. And that conserves charge we mentioned, it acts like a permanent lock on a door, preventing it from ever decaying. It's basically a loophole in physics that allows these strange clumps of energy to exist. And this is exactly why Q-balls are the target of our cosmic hunt. Our current rulebook for physics, what we call the standard model, it has no place for them. But other, more advanced theories, like supersymmetry, or SUSY for short, they totally predict that these things should be out there. So finding a Q-ball wouldn't just be interesting, it would be the smoking gun for a whole new, deeper layer of physics. All right, so we have our suspect, a tiny, incredibly stable clump of pure energy. Now, what happens if one of these things grows to a colossal size? Or what if trillions of them gather together under their own gravity? Well, then you get a Q-ball star. A Q-ball star is exactly what it sounds like, a star-sized object made from this quantum weirdness. It wouldn't be a ball of fire and plasma like we're used to. No, it'd be something far, far stranger. A giant, stable ripple in the very fabric of space-time itself. And its properties would be truly mind-bending. For one, it's cold. No fusion burning at its core. It's dark, almost completely ignoring light. And get this, it wouldn't even have a surface. Its edge would just be this fuzzy, gradual fade-out of its energy field. Can you imagine flying a spaceship towards one? You might not even know you'd entered it until its gravity really took hold. But the plot thickens. Of course it does. The mystery doesn't just end with Q-balls. There's another suspect in our lineup of cosmic oddities, a close relative called the Fermi-ball, and it adds a really fascinating new layer to this whole case. A Fermi-ball is a hybrid. It basically takes the energy field container of a Q-ball and then uses it to trap actual particles, fermions, the very building blocks of matter, like the neutrons you'd find inside a neutron star. So now you've got this strange brew of both a quantum field and conventional matter, all working together. The crucial difference here is what's stopping them from collapsing under their own gravity. A pure Q-ball is held up by its own internal field forces. A Fermi-ball, though, it relies on something else entirely, Fermi degeneracy pressure. That's the same fundamental quantum rule that prevents all the electrons in an atom from crashing into the nucleus. It's this incredibly powerful hands-off rule for matter. This quote from the source material really just nails it. A Fermi-ball star isn't quite a neutron star, which is made of pure matter, and it isn't quite a pure Q-ball star, made of a pure field. It's this unique, stable blend of the two. Okay, so this is all fantastic in theory, but it leads to the billion-dollar question for any cosmic detective. If these things are dark and cold and basically invisible, how on earth do we prove they're real? I mean, where do we even point our telescopes? And here is the stark reality of our investigation. The number of confirmed direct detections of any of these objects is a big round 0. We haven't found a single one yet. And you know what? That just makes the hunt all the more thrilling. So, astronomers have to be clever. Since they can't look for light, they look for gravity's fingerprints. They can hunt for something called lensing, where a dark object's gravity acts like a cosmic magnifying glass, bending the light of a star behind it. They can listen for a unique chirp in gravitational waves if two of them happen to collide. Or they could spot tiny wobbles in the timing of pulsars, which are basically the universe's most accurate clocks. Let's just step back for a second and consider the stakes of this whole investigation. Why are we even chasing these cosmic ghosts? Because finding just one, wouldn't just be some small incremental discovery. It would fundamentally rewrite our understanding of pretty much everything. The fallout would be immediate, and it would be revolutionary. It would prove the existence of new quantum fields we only dreamed of. It would offer the first hard evidence for ambitious theories like supersymmetry. It would mean we've discovered a completely new and stable form of matter. And yeah, it could finally crack the case on dark matter, one of the biggest unsolved mysteries in all of science. That's all it would take. One. A single confirmed signal from a Q-ball or a Fermi-ball wouldn't just add a new object to our astronomical catalogs, it would trigger a complete revolution in fundamental physics. It would prove that the universe is far stranger and way more populated than we ever dreamed. And that's really the heart of it, isn't it? These aren't just another type of star to classify and put in a textbook. Finding one would be like discovering a new state of matter for the first time, like when we first understood solids, liquids, and gases. It would confirm the existence of a whole new state of reality, hiding out there in the cosmic dark. And that really leaves us with one tantalizing thought. What else is waiting to be found?